So today I'm going to talk about this topic, gravitational waves from phase transitions and PTAs. This will not be exactly a lecture, it will be more like a talk. So I typically try to follow the advice of the esteemed previous speaker, and once in a while, at least, I do something new. So especially the second part is also new to me. It's kind of, I'm still learning. So I'm happy for feedback and also a lot of questions. I try to go slow, but yeah, let's see what happens. Okay, so I flashed this yesterday, and today we're going to talk about this third part. So we already had a picture about pulsar timing arrays previously. And the main idea here, again, is you have certain pulsars, and these pulsars work as really, really precise clocks. So they are millisecond pulsars, and you can time these pulses. And it turns out if you do this really carefully and also have a good model for the deterministic part, because it's moving and so on, you actually can time this down to nanoseconds. Right? So these are really, really precise clocks. Now the idea is if a gravitational wave is passing through between you and the pulsar, you can use these pulses or residuals in these pulses in order to detect these gravitational waves. So in the latest data release, NANO-Grav reported that they've seen an excess in what they call common red noise, right? And this would, in principle, fit the bill of gravitational waves. So you see something happening in all the pulsars, and it's red tilted, so it's more prevalent at small frequencies. And this is also what you expect if you have a background of astrophysical origin, for example. So the first question is, of course, is this really gravitational waves, or is this just misunderstood noise? And the litmus test in order to decide this is, of course, the Helling-Downs curve, which we've also seen previously. So the point here is if you not just look at one pulsar, but if you look at pulsar pairs, then you can improve your measurement because the noise will be uncorrelated. And on top of it, because you know that gravitational waves come from quadrupole radiation, you also know that it will depend on the opening angle, how these the two signals in the two pulsars are correlated. And the Helling-Downs curve shows this exactly. So on the x-axis, there's a separation angle between the two pulsars in the pulsar pair, and on the y-axis, there is the strength of the correlation of the measurement. You see that there is a certain dependence. And as I mentioned before in some of the talks, actually you don't get the same for 0 and 180. So the PTA is even sensitive to the direction of the gravitational waves. So it makes a difference if the gravitational wave is coming from this direction or this direction. So in the PTA you see difference, while in ground-based experiments you can't distinguish these two sources. All right, so of course I'm interested in phase transitions. So the question is, can phase transitions explain the source? And I showed you all these simulations last time, and the most important information in the business is what is the spectral information here. So how does the spectrum behave, and what are the different exponents in the spectrum? And we had this result that there are two physical scales in these spectra, one coming from the bubble size, that's this knee here, and one coming from the shell thickness, which makes the peak. And when you make the fit, what you will find is that at small k, the gravitational wave power spectrum scales like k cubed, and there's a plateau between these two, between the knee and the peak, which scales like roughly k to the 1, and then there's a tail which scales like k to the minus 3. Right? And of course, then the obvious question is, can you fit this kind of spectrum to the data which is seen by a NANO-Grav? And this is explored here. So what this flow shows is two things. So on the y-axis, there's the amplitude of the signal that you see. So this common red noise. And on the x-axis, there is a fit to the spectral index. So the slope of this power spectrum. Right? So there's one prediction from supermassive black hole mergers, which is 13/3. No, 13/3 in terms of strain. Then the blue one are predictions of a simulation suit of mergers. So if you change the environment of these super black hole mergers and some other parameters, you don't get exactly this 13/3. You get kind of a certain range in parameter space and also a certain flexibility in amplitude. This, of course, depends on the merger rate, how often these mergers are expected. And the measurement is shown here in green. Right? And the observation here is that it's not a perfect fit. So it seems that the slope seems to be a little bit too shallow, right? And also the amplitude seems to be a little bit too high for what people expected for supermassive black hole mergers. So now, next question is, of course, how does phase transition fare in this kind of comparison? And to indicate this, I've shown you the two slopes that we get from the simulation, the k to the 3 and the k to the 1, in kind of these units. And the infrared tail, the k to the 3 would be a 2 in gamma, and the plateau, the k to the 1, would be a 4 in gamma. So basically, the in-between region between the plateau and the infrared tail, which means exactly the knee, will give you something in between these two scales. So there's no problem here to fit the power spectrum of this form to the NANO-Grav data. It will give you a perfect fit, right? So if you just do the fit, your fit ends up exactly in the middle of this ellipsoid. Right? Okay, but this is, of course, misleading, right? Of course, you are cheating a little bit. This is not a fair comparison, because in BSM, you have a lot of freedom, right? You can choose the amplitude at will, right? You can choose the temperature at will. Because of all this freedom, in principle, you can make this fit work really, really well. So I would say, even though I'm, of course, doing BSM and phase transitions, the gut feeling is this chances that this is really BSM is perhaps like 5% or something, right? And it's really, really likely that the actual explanation is astrophysical. Right? And it's just not well understood why the prediction is here, not here, or perhaps also the measurement will move a bit in the upcoming years. Okay, so, but then the question is, so is there a way to distinguish these kind of classes of sources by other means, not just looking at this plot? And if you think about it, I came up with like 5 ways of potentially distinguishing these two sources. And one we just discussed, that's the shape of the power spectrum. But I'm not really optimistic that this will be the deciding factor, because we as theoreticians, of course, really inventive. So whatever happens on the experimental side, we will find a way to accommodate this. So I don't think there will be anyway ever a situation where NANO-Grav reports something and the theoreticians say, okay, we give up, we cannot explain the signal. This will probably not happen, at least not on the level of the power spectrum. The second method would be to look for isolated point sources. So if it's really astrophysical, it might be that there's one event which is really, really close by and completely dominates the signal. Right? If this happens, you should pick it up in the data. And NANO-Grav does searches for these isolated point sources. So these are called continuous wave searches, and they haven't found anything yet. But in principle, they could find something with the next data release, and this would indicate that it's probably rather astrophysical and for sure not cosmological background. So more generally, if it's not just one dominant source, you could think in terms of anisotropies. So if it's really astrophysical, you would think that there are anisotropies, while if it's really primordial, you would think it's a stochastic background, and typically people would say that the stochastic background doesn't have any anisotropies. Besides that, of course, you can also think a little bit harder about particle physics. So imagine you do a particle physics experiment like a beam dump or something else, and you find a particle, and then you figure out the properties of this particle, and you see that there will be a phase transition in this kind of model. Then you, of course, have a lot of support for the theory that this phase transition might explain this, explain the signal. And the last point that you eventually might do is you can cross-correlate with other gravitational wave signals. So, for example, if you see something in LISA, right? You've seen the spectra from the cosmic strings, which give a rather flat spectrum. So if something is a NANO-Grav, you should also see something in LISA, right? So if you see also a background in LISA of similar sizes, would be a strong indication that it's rather cosmological and not astrophysical, which typically lead to a spectrum that is going down at larger frequencies. Okay, so I think, and many people in the field believe, that the best way to really distinguish between a cosmological and an astrophysical source are anisotropies. And actually, NANO-Grav already did an anisotropy search in the last release. And this is kind of the money plot. So what you see here is they did an expansion of the sky in terms of spherical harmonics, and they plot the coefficient of these spherical harmonics as a function of the frequencies. And this gray band are kind of predictions of these holodeck models, which I've seen before, this blue dot. And the dotted lines, the colored dotted lines, are measurements. Okay? And the conclusion here was that no anisotropies have been seen. But in principle, you see already a couple of points start to be lower than what is expected. So at some point, this search might be sensitive. So there's a lot of discussion in the community about this plot. I will not comment much more about it, but basically this plot got us interested to have a closer look into what's going on and how the story with the anisotropies works. Okay, and this leads to a different one aspect of this anisotropy search, and that's cosmic variance. So there were a couple of papers by Bruce Allen in the literature about cosmic variance of anisotropy searches. I mean in general, but also in anisotropy searches in PTAs. So we looked at these papers, and the message seemed to be that cosmic variance might play a role, and we wanted to understand to what extent does cosmic variance enter in this analysis by NANO-Grav. Okay, so this is heavily inspired by this paper by Bruce Allen. Okay, so in the following, I will really relatively slowly, so I have a timer, still plenty of time. Relatively slowly walk you through the derivation of the Helling-Downs curve and how interference and cosmic variance enters in this kind of analysis. Okay, so what you observe is a time delay in these pulses, right? And when you do the math, what you find, okay, there are different ways of writing this, but at least to me, the most physical way to write the outcome is that the delay is basically an integral over the metric along the geodesic of the pulse, right? And then it's projected on the direction of the pulsar. So HIJ is a spatial part of the fluctuations in the metric. So you project it on the direction of the pulse, and you integrate over the geodesic. So this is the time and the location of the pulse while it follows the geodesic from the pulsar to Earth. Right? Okay, so now at this stage we want to make an ansatz for what we expect for Hij, and this is just a plane wave ansatz. So we say Hij is just a sum of plane waves with different frequencies, different polarizations, in different directions. So this is just an ansatz. We just say, okay, Hij is just a collection of waves, and you can always Fourier transform your Hij, so this is true in principle in general. So E here is the polarization, which comes out of the Hij, and in principle, not in principle, it's always orthogonal to the direction of the gravitational wave. Right? So Eij is orthogonal to omega hat in our notation. Okay, so you plug back this expression for H into delta t, right? So you know that the time and x dependence is this one, so now we can do the integral. And what you get is, again, now we still have to sum our polarizations, directions, and frequencies, because this was our ansatz for the fluctuations. Then you get still a time dependence, and then you get a function R, which is called the response function. So the response function has two terms, because you do an integral, right? So you get one contribution from both boundaries, and accordingly, these two terms are called Earth and pulsar terms. And then you get a function in front, which basically contains the projection of the tensor on the direction of the pulsar, and this prefactor 1 plus omega times p. So I remind you, omega is the direction of the pulsar, of the gravitational wave, sorry, and pa is the direction of the pulsar with index a. One comment here, so in principle, if you look at this expression, sometimes or often in the analysis, this pulsar term is neglected because people say, well, it's a phase, right? So in average, if you have a lot of sources and a lot of pulsars, so in average, this pulsar term will be 0 and then it's neglected. But in principle, this pulsar term is a correction of order 1, right? So that's why we keep it for now. Another comment, this guy might look a little bit strange, right? Because in principle, you can go to the limit where omega times p is -1, right? So in the notation is a bit strange. So omega is the direction of the gravitational wave, right? and p is the direction from Earth to the pulsar. And that becomes -1 when the gravitational wave, when you are looking exactly head-on to the gravitational wave that is traveling to you. So, yeah, when you look at this expression, you might wonder, well, what happens actually when this guy becomes 0 and this f function blows up? Okay, so what happens is relatively simple. So you just look. This guy will be small, but also this guy will be small, right? And if this guy is small, you can just expand this exponential function. Then it's 1 minus 2 pi a blah, 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 blah. The 1 will kill this guy, right? And then you can kill this function against this prefactor. Right? So in the limit where p goes to minus omega, the response function actually becomes L times the projection on the polarization tensor, which means that the response function becomes linear in the distance between the pulsar and the Earth. And this is kind of intuitive because it's basically dissociation. So let's say you have Earth, you have the pulsar here. So the pulses are traveling this way. And now this would be the vector p, right? This would be the vector omega, right? So basically what is happening that you have this wave. The wave is traveling in this direction, and the pulse is surfing the wave, right? So the wave is moving this way, and the pulse is just moving with the wave, right? So basically the H field, the fluctuation that the pulse is seeing in this integral here is constant, right? And because of it, the integral will become linear in the distance. So this limit is perfectly fine. Actually, this limit is also perfectly fine for a different reason, because if you have p and omega collinear or anti-collinear, right, then this guy will become 0, right? And the reason is if the gravitational wave is traveling in this direction, the deformations are like this, right? They are in these two directions, so the pulse will not see any of these deformations. So this limit is perfectly fine. Let's consider another limit, which was asked at some point in another lecture, the large wavelengths or small frequency limit. So now we take the limit where L times omega is small, which means, this should be F, sorry. So this means this guy is small, so you can again do the same trick. You can expand this guy, and then you get for the response function again this expression. So this is now the general expression, which always works in the large wavelength small frequency limit. And it shows you that in this limit, the sign of p doesn't play any role. So you can flip the sign of p, right? Or you can flip also the sign of omega, and nothing will happen. Which means in this limit, the detector will not be sensitive to the direction of the gravitational wave. Actually, there's a good reason why, for example, ground-based experiments are another reason why they're not sensitive to flip or the direction of the gravitational waves. And that's because in the ground-based experiment, you always get the phase shift from a round trip, right? So the light is traveling to the mirror and back. So if it travels this way or this way, of course, doesn't make a big difference. While in the pulsar, in the PTA, it's a one-way travel, right? So you just pick up a phase, and this is also essential in the fact that the direction actually is relevant. Okay, so what we want to measure now is, like I explained before, this Helling-Downs correlation. And what we do here is what's called a Broadband. So what we do is we take the time residuals in two pulsars, so A is not B, and then we integrate over these residuals over time. Okay? And if you plug in the expression we had, then you will find kind of a horrible mess. So there are a lot of sums here, because each of these guys is a sum over the direction of the sources and the polarizations and also the frequency. You get 5 sums here. So the sum over the frequency is actually only a single sum, because if you do the integral, then the frequency in both sources has to be the same. Otherwise, you don't get a contribution. But otherwise, you have a double sum over the directions, right? And also a double sum over polarizations. So now in this business, what's often done is just to consider the diagonal contribution. Just the contributions where k is equal to k prime and a is equal to a prime. And this is because if you have a stochastic background, then in the ensemble average, this is true. So on the ensemble average, you only get a contribution if k is equal to k prime and a is equal to a prime. And this motivates people often in the first step of the analysis to neglect these additional terms and just reduce to k equal to k prime, a equal to a prime. This means essentially that what you do is you neglect interference. Okay? So the question I want to answer in the last 20 minutes, or even less, is to what extent is interference between different sources important? Okay, so just to give you an idea, I want to explain in which limit you actually get Helling-Downs. So Helling-Downs you can get in two limits. So the first limit is if you neglect interference from the start. So assume you have a lot of sources, many sources on the sky. You neglect interference, which means that this product becomes actually a delta function, and these double sums become sums over k and a. Okay? So if you use this information, then you will find that the cross correlation is proportional to single sums over k and a of these response functions. And you can show that in this limit. You can also figure out that the interference from the pulsar term is not important. So this is roughly twice this f function, and this is exactly the Helling-Downs correlation. Yeah? So if you neglect interference and have many sources, what you get is exactly Helling-Downs. There's a second limit where you get Helling-Downs, and this is if you have a single source, but have many pulsars, and then bin over pulsars with the same angular separation. Okay? So let's say you have 1,000 pulsars, you have a million pulsar pairs, you take all the pulsar pairs which have the same opening angle, and average over them, and of only a single source, also in this limit, you get exactly Helling-Downs. Okay? So what these two examples share is that interference is completely irrelevant, right? In the first one, we neglected interference just by assumption. And in the second, we have a single source. And because there's a single source, there's no interference. Okay? And in both of these limits, one can find that the outcome is exactly Helling-Downs. All right, so all of these things are not new. This has been figured out and really nicely explained in this paper by Bruce Allen on the variance of the Helling-Downs correlation. But I would like to understand what is the implication of this for the anisotropy series. To give you an idea why this is important, I want to consider two limits. So the first one is, again, a limit where I want to measure. So imagine you have now a model, which is called a Gaussian ensemble, where you have a sky, you pixelate your sky, and to every pixel you assign a certain amplitude. And the amplitude you just take from a Gaussian ensemble, right? And the question is, what is the power you're going to measure? Okay. So the power is the product, is basically this product here, it's HH star, right? And basically now in every pixel, you know the power, but the power, of course, is still has a relatively large variance in the sky. Right? I mean, the amplitudes are Gaussian, right? Which means that the amplitude, the real and the imaginary part of the amplitude are Gaussian, which means that the amplitude is Rayleigh, and this means, strictly speaking, that the power is a chi-square distribution. Right? So in every point, you have a distribution which has a certain mean, and the variance which is as large as the mean. But now consider the case where I coarse-grain this map. So now instead of having all these small pixels, I make larger pixels, and I average the power over these larger pixels. So how will this picture look like? Well, the mean, so the total power, will basically scale with the surface of these larger pixels, right? But the standard deviation will only scale with the square root of the pixel size. And because of it, if you let's say, average over 100 pixels to go from here to here, the sky will look really homogeneous. Right? This is basically why people think, even if you start from a Gaussian ensemble, which looks really noisy on really smart skies, as long as the scales are small enough, the outcome will be really homogeneous. So this means if interference is neglected, the stochastic source will look isotropic in terms of power. So now we want to add interference. And this means, if you go back to this equation, we want to not average over power, but we want to average over the amplitudes, okay? So if you now do the same thing, so you have the sky with many, many small pixels, you assign Gaussian distributions to the real and imaginary parts of your amplitude, and you average over this, what you get are still Gaussian contributions, right? And if you do this, and then calculate the power afterwards, what you get are still Rayleigh distributions, or chi-squared. This means the variance in the power is still of the same size as the mean of the power. So this means, if you include interference between the different sources, the coarse-grained sky will actually look not isotropic. It will look really, really patchy. And this is, of course, one motivation to include the interference in the analysis. Okay, so there's a different way of seeing this. And here I'm not doing any coarse graining. I'm not doing anything fancy. I just evaluate this guy, keeping different terms. So what I show you here is, again, the 2-point function as a function of the opening angle, so from 0 to 180, where I neglect different terms. So the first one is the yellow dots in the background. These are always the same. That's the full result. So I just take, I sample my Gaussian sky, and I evaluate this guy, right? So now in the top left, I do the same, but this time I neglect certain terms. So I have, it says only K interference, but what I mean by that is that I neglect the interference in the different polarizations. So I say this guy is diagonal in the polarization, so there's a delta AA prime, and I also neglect the pulsar term. And what I get is this, and you can measure that the variance here is roughly half the variance of the full variance. Another thing you can do is switch everything off, but the K interference in the pulsar term, and what you see is that the variance is roughly the same variance as before. So the two most important things here seem to be the K interference in the pulsar term. The K interference has a large effect. So the next question is, do the pulsar terms by themselves have a large effect? And the answer is no. So if you neglect K interference, so you have a delta KK prime, but you keep the pulsar term, then what you get back is still exactly Helling-Downs, right? So I'm not doing any binning here. So these are exact results. So basically that everything collapses to Helling-Downs is because of this limiting case where you have many sources but neglect interference, right? Okay. So you can also take the same data and show this in a different way. That's what we do here. Because Bruce Allen here also basically proposed to split the total variance in two different components. And one component he calls pulsar variance, and that's a variance that limits in the limit of infinitely pulsars. So if you have infinitely many pulsars, or if you average over pulsar positions, then the pulsar variance goes away. But even if you do that, there's some variance left, and that's what he calls cosmic variance. So cosmic variance does not vanish in the limit of infinitely pulsars. It also does not vanish in the limit of infinitely sources, right? So what you have to do in order to get cosmic variance to vanish is to do the ensemble average, right? If you have only one representation, even if there are many sources and many pulsars, there's still cosmic variance. So what you see here, this band, is exactly this cosmic variance. So what we do is we average over basically pulsar directions, right? And then the variance which is left is this cosmic variance because we have only one representation in our calculation. So when you do this calculation, or what we found is this double dip structure, and that was also predicted by Bruce Allen. So you can go back to the paper by Bruce Allen, and you will find exactly this expression. Ours is a little bit smaller, because we have the broadband expression, while Bruce is doing it for only one frequency. Okay, but also this result is not new, okay? This was also known in the literature. Now, the next step is to somehow close the gap to the analysis in NANO-Grav of anisotropies. So they have different analysis, but what I'm gonna discuss is one analysis, a frequentist method of getting a p-value for the probability that there's an anisotropy. So it works as follows. So you cook up a likelihood function, which is a Gaussian function depending on rho. So rho is now these 2-point correlations. So for example, if you have 50 pulsars, then rho here will be a long vector with all the 1200 cross correlations. Then P is the power in the sky, right? So for example, you could use a pixelation, or you can also use spherical harmonics. And R is again a response function which is proportional to the square of the response function we had before. So now if I give you a rho, you can minimize this function with respect to P. And that's what's called sky reconstruction. So for every rho, you can reconstruct the most likely sky map. Okay? Next, what you need is a detection statistics. So you want to ask the question, how likely it is that what you're seeing is actually a homogeneous sky? Because here we only discuss power, right? So in this language, stochastic background would mean there's homogeneous power. Okay? So your detection statistics is the square root of the 2 times the logarithm of this probability. So I give you a rho, gives you a sky map, divided by the probability. I give you a rho, you give me the most likely homogeneous sky map. Okay, that's what's called, this is isotropic. So this is the probability of the most likely homogeneous sky map compared to the probability of an arbitrary sky map. Okay? So if I give you now a rho, in principle you can give me an SNR. Okay? And let's say this SNR 3. So what does this tell you? Well, at this stage you don't know. Why? In the measurement there's always noise. Okay? So at this stage you would like to know, is this anisotropy that I'm going to measure, is this from the noise or is it from the data? And how do you do this? Well, you construct a null distribution, meaning you take a model, which in this case is the 2-point correlations are Hellings and Downs, plus the noise, so you know the noise from measurements. And now you just feed this into the SNR and you get a null distribution. This is a distribution of SNR that you expect for an homogeneous sky. And now if I give you again some 2-point functions, you can see how likely it is that this is actually a homogeneous sky. Okay? At least this is the idea. However, we believe this is not a good model. Why not? Because in principle here, the cosmic variance would enter, right? So this correlation is not just Hellings Downs plus Gaussian noise. Another reason is, in principle, these guys are not independent. Right? So there should be a cross correlation. So this Gaussian noise is independent. I mean, this is just a one big vector, right? But there should be also cross correlation between, let's say, rho 1, 2 and rho 2, 3, because both of them involve the same pulsar. And this is also neglected. So the argument to neglect this is, of course, that the noise in the instrument is still relatively large. And you would think that in this limit, all the other effects are irrelevant. But of course, you can also just do the math and check. So what we did is we took our model, this guy, we sampled this guy 1,000 times. We go here. So instead of Hellings Downs, we now have our quantity including the cosmic variance. We add the instrumental noise and follow the same procedure. And by doing that, we get a second null distribution. And the outcome is this. So the red one is a null distribution that NANO-Grav used in their analysis. And the blue one is a null distribution if you include cosmic variance. And for example, one way to read this plot is, if in the NANO-Grav analysis, they would say, okay, if SNR is larger than 4, we are in this tail. This looks really unlikely, right? So we detected an anisotropy. But if you look at our distribution, if you measure an SNR of 4, this is still totally in the middle. Right? And physically, the point here is, because if you include the interference, the sky looks already quite patchy. And it's just really, really hard to compare this patchy random sky from a sky which has actual anisotropies. Right? This makes it much, much harder. All right, so you can also do something which is a little bit more sophisticated. For example, you look at hotspots. So here what we do is we cook up a sky where all the pixels have the same power, but there's one hotspot which has 30% of the total power. And we ask the question, how does the old method fare compared to the new method? So the method without cosmic variance compared with the method with cosmic variance. And you see if you have one hotspot, both methods give you really, really similar results. And this is not too surprising, because if you have one hotspot, there's no interference. And if there's no interference, cosmic variance is not so relevant. But of course, one also has to say, in some sense, if this is really the world we live in, then this will be picked up by this continuous wave search I mentioned, long before the anisotropy search will find anything. Okay? So this is actually not the interesting case. So now consider a sky where you have 3 hotspots. So each of these hotspots have 20% of the total power. And we again ask the question, what is the sky reconstruction in the two methods with and without cosmic variance? Okay? So and if you include, if there's no cosmic variance, then the method reconstructs the hotspot, this one really, really well, and this is a little bit worse, but this is of course because there are much more pulsars in this regime, right? So you see most of the NANO-Grav pulsars are in this hemisphere, right? But once you switch on interference, then the interference between these 3 hotspots kind of completely spoils the detection. Yeah? You see the darkest region is now here. There's still some probability here, but somehow the method completely fails to see any of the hotspots. Okay, this brings me to the conclusions. So we concluded that neglecting interference in the null distributions seems to lead to inflated p-values. So this should be definitely included. Overall, including interference, I mean, it's not about including interference. I mean, there is interference, right? So this makes it really hard to distinguish the stochastic Gaussian ensemble from an astrophysical one, for example, in case of hotspots. Actually, Gian Massimo pointed out a paper to me, which was briefly before Christmas, where it was noticed that unlike in the CMB, I mean, the CMB, this is kind of a completely irreducible problem, right? You measure one CMB map, and it is what it is, and we only have one, and that's it, end of story, right? So because of it, you have a large uncertainties in the small L's. Here, in principle, you have the possibilities to measure different sky maps at different frequencies. So if the accuracy improves and the noise goes down, in principle, you could, let's say, measure 10 sky maps and average them, and the average of them will approach Helling's down, right? So in principle, what's called cosmic variance here is not really totally irreducible, because here you can in principle reduce it using different frequencies. However, realistically, this will take much, much more data, because we are not even in a stage to see the anisotropy. I mean, we haven't seen anything, right? We haven't even seen the anisotropy. I mean, if it is really a Gaussian ensemble, we haven't even seen the patches from the Gaussian ensemble, right? In order to see true anisotropy would take much, much more data. Okay, so as promised, I'm finishing before the end of my time. So I guess it's time for lunch. Thanks a lot.
Yeah, thanks, Thomas. Yes, Anish.
Yes, and thank you for the nice talk. So I have a couple of questions, which, I mean, we had a discussion on pulsar timing array and Hellingstone last week also. So I'm going to repeat the question that we had.
You have an advantage, I wasn't there.
So one of the things I was wondering, in particular in the context of anisotropy, so if I assume that the stochastic gravitational waves is coming to us is chiral, in the sense that its left-handed polarization has something offset with the right-handed. So I can have some sources, right, from preheating of the source. So do you expect, particularly for those cases, to have some more features in the primordial
So
anisotropies?
If you consider chiral sources, I mean, in our language, we have the 2 polarizations, right? And in principle, a chiral wave would be one where the plus is I times the cross, right? Mm-hmm. But in general, we find that the interference between different polarizations doesn't play much a role. You can see it basically in this plot. So in this plot, the interference between different polarizations is neglected, because this only includes interference between different directions and the pulsar term. So I completely neglect interference between different polarizations, and the variance doesn't change much.
But at the level of anisotropies, do you find them back because of
Yeah, I mean, this is a major problem, right? I mean, the question is what you're going to do with this function, because here in this whole method, probably it's completely ingrained that interference is neglected, right? Because this analysis is already on the level of the power spectrum. I mean, as long as you use the proper null distribution, this is technically speaking not a problem, but what you might do here is just suboptimal. So let's say if you would encode the amplitudes in your likelihood function, right, then you might do a much better job because you keep more information in your analysis, right? So already the reduction to power here is kind of a problem. But if you, I mean, of course, it's something we tried, at least tentatively. And if you do this, the problem is then this guy is quadratic in the amplitudes, this guy is quadratic in the amplitudes, and then you have to find a minimum of a quartic polynomial, right? Finding the minimum of a quadratic polynomial is trivial. Finding a minimum in a quartic polynomial is not trivial because there are many, right? Mm-hmm. So typically you get, in your search, you get stuck somewhere. And the sky reconstruction is really poor as well, right? Because the mechanism just doesn't find the right minimum of the likelihood function. But in principle, that's what you would have to do in order to become sensitive to these kinds of questions.
Thank
you. Yes.
Sorry, since you said something about not finding anisotropies, we put out a paper on the 13th of December with mere time, and
I was on vacation. But I will check it out.
You might be interested. At 7 nanohertz, there seems to be something, but we're not quite sure if it is.
So say it again. So what are you doing exactly?
So this is data from the mere time PTA. With 83 pulsars, we do seem to find some hints of anisotropy, but it clearly needs a lot more work. But the paper is really new.
Yeah. So what are you using in terms of methodology? So you use this kind of thing, or?
It's the usual spherical harmonic decomposition.
So square root, spherical harmonics.
And very similar to the NANO-Grav analysis with some marginal improvements. But we can chat about that if you want. But there are some PTAs which might be seeing anisotropies, but it could also go away with some noise modeling. Right. So this is a common feature in PTA data, that often noise modeling will rob you of results. But it's out there if you're interested.
I'm very interested. Let's chat.
Any more comments, questions? If not, then let's break for the lunch. Okay,
thanks.
And we resume at sharp 2:30. Thank you very much. Thank you.